Maastricht. Please be seated.
Hereby, I open this academic ceremony in which Gözde Şahin will defend the academic thesis Small Things, Big Impacts, Guiding Cell Fate Through Next Generation Microengineered Systems. May I invite you to present a summary of your study and the conclusions of your thesis.
Dear Prorector, dear members of the committee, dear colleagues, friends and family, thank you for being here today. Now I will briefly summarize my research entitled Small Things, Big Impacts, Guiding Cell Fate Through Next Generation Microengineered Systems. The human body is an extremely complex system. Every action we take, breathing, eating, sleeping, requires coordination between almost 100 trillion cells with about 200 cell types in different organs. And these cells don't just exist, but they constantly interact with their environment and respond to every signal they receive. When the right signals come in the right amounts, at the right place, and at exactly the right time, they organize themselves into tissues and organs of different size, shape, and functions. While we know genes and proteins are important, the precise regulation of this process is not fully understood, and scientists are actively working to uncover these mysteries. What if we could create tiny but precise models of human tissues in a laboratory, almost as if we had a miniature version of these tissues and organs in front of us? These models could have scientific potential. For instance, they can provide deeper biological insights into organ development and disease modeling with the possibility of serving as alternatives to animal models in drug development. Because of the complexity of creating such models, this requires multidisciplinary approach, and one of the approach is combining microtechnology and biology. Microtechnology has changed the way we study and manipulate cells. It allows us to develop microengineered systems with precise control over chemical and physical signals. By changing these signals, we can mimic the environment that cells experience, and essentially making them almost feel at home. The closer we mimic the natural condition, the more accurately we can study and predict the mechanism of biological processes. And this is what I focused on in my thesis. By combining different microfabrication techniques and materials, I developed microengineered systems that can guide cells to potentially form functional tissues. And my thesis starts with a general introduction, following by two literature reviews. These reviews in chapter 2 and 3 gives overview of current microfabrication techniques for increasing the surface complexity of cell material interfaces. Then it follows with experimental chapters 4 and 5, where I designed systems with precisely defined surface topographies to mimic the morphology of native tissues. Then in chapter 6, I introduced a system that mimics the mechanical forces cells experienced in their natural environments. And finally, in chapter 7, I presented a pilot study where I showed the fabrication of a microfluidic system which generates concentration gradients to guide cell behavior. To start with chapter 4, we explored the importance of dimensionality for corneal cells. The cornea is the outer part of the eye and provides most of its refractive power, mainly due to the stroma, which is a layer with well-organized collagen fibers. Corneal cells called keratocytes maintain this complex structure, but they can also produce disorganized collagen when they are activated due to injury or disease, and this leads to vision problems. Therefore, it's important to carefully guide keratocytes during tissue repair. And one approach is to identify key features of complex geometric patterns of native tissue and incorporate them into cell culture. But the question is, how can we accurately identify those features? To do so, we use the reductionist approach. Imagine a football stadium. In 3D, the stadium has a field, different levels of height, and is more complex and detailed. When we simplify it into 2.5D, we can think of it as a ring-shaped geometry where some heights and shape remain, but with fewer details. Then we reduced it even further to a flat 2D surface, focusing only on the field and removing the height, like we are viewing the football field from above. And this is what we also did with cornea. We simplified the native 3D stroma architecture into 2.5D and 2D surface patterns by gradually reducing the height component. And these patterns varied in both width and height, allowing us to pinpoint the dimensional requirements. What we found is that while 2D topographies can guide corneal keratocytes, eliminating the height component removes the crucial signals necessary for keratocyte orientation and their collagen deposition. And this shows that we can simplify the architecture to a certain extent, and further reduction in complexity results in the loss of essential cues needed by corneal cells to function properly. In the next chapter, we introduce the multi-replication process. This image shows a small section of the human cornea and magnified 20,000 times, showing its dense and fiber structures where cells are located. And just like other native tissues, it has porosity which allows oxygen and nutrients to reach the cells. And now, if we look at the second image, you will see something similar. It's a fiber mesh structure made using a technique called electrospinning. Electrospinning is a powerful technique that can produce fibers mimicking natural tissue architecture on a large scale and at a low cost. However, because of the random fiber deposition, it is difficult to reproduce the exact fiber position even with the same experimental conditions. And producing identical structures with different materials and porosities is even harder or simply not possible. Also, fiber size, density, and porosity are all linked, making it difficult to independently adjust these factors for systematic cell culture applications. And to overcome these challenges, we used electrospinning to create fiber meshes that mimic the structure of native tissue matrix. Then we used imprinting to replicate the surface of this architecture onto different polymer films, which could be used for cell culture applications. And this process is very exciting because it allows us to decouple fiber textures from the material properties. If you look at the first row of this microscope image, you will see that we created dense fiber meshes having different fiber diameter and orientations. And in the second row, we used that electrospun fiber mesh as a template to create molds with inverse fiber patterns, which we then used to replicate those patterns onto different substrates. The third row shows the fiber textures after imprinting on polycarbonate film. We have also transferred these structures onto polystyrene, polymethyl methacrylate, and cyclic olefin copolymer, which are all suitable materials for cell culture applications. Our process opens up new possibilities, such as decoupling fiber diameter and bulk porosity. Using the same molds, we can imprint these structures onto substrates that has predefined porosities. And in this case, we used polycarbonate films with initial pore diameters ranging from 2 to 12 micrometer. This allows for the independent tuning of fiber size, morphology, and substrate porosity, which was not possible to achieve before. Also, we now have the ability to overlay the same fiber textures onto physiologically relevant substrates. Using thermoforming, we shaped fiber-imprinted polymer films into molds, which allowed us to transfer the fiber patterns onto different non-planar substrates, such as microchannels and microvalves. We were able to achieve precise control over the alignment of the fibers, whether they were parallel or perpendicular to the long axis of the microchannel, or placed on the inner or outer surface of the microvalves. And in the end, our multi-replication process allows for the creation of large-scale fiber template libraries and ensures the consistent reproduction of fiber arrays on both flat and curved surfaces, and across a different type of materials and also different surface properties. In the next chapter, we create platforms to apply mechanical stimulation to organoids. Organoids are three-dimensional cell aggregates that mimic key functions of organs in vitro, and they can be visualized as green beads in this illustration. Typically, they are cultured inside a dome-shaped droplet of hydrogel, and they are randomly scattered within this gel-like structure. Now, imagine applying a mechanical force to this system by constantly stretching and releasing the film underneath the gel. Because they don't have a fixed position, the organoids will begin to move randomly within the gel, making it impossible to consistently track each one from the start till the end of an experiment. Also, because of the random movements and their position, the organoids will be exposed to inconsistent mechanical signals, which can influence their behavior and function. To address this, we have designed a stretchable millival array with designated pockets that can hold each organoid in a defined space. And this setup ensures that all organoids receive uniform mechanical signals and remain in a fixed position during mechanical stretching. And to develop our stretchable millivalves, we used thermoplastic elastomers, which has been largely overlooked in dynamic cell culture applications. And the main advantage of these materials is that, unlike commonly used elastomers, its thermoplastic property makes it suitable to produce in large scale. And to show this, we use fabrication techniques that are commonly used in industry, including compression molding and thermoforming, and produced either flat or millival films, and integrated them into a cell stretching device. After installed, we were able to apply one-directional or two-directional stretches to the films. To test our system, we used intestinal organoids and simulated the peristaltic motion, which is contractions that move food and liquids through the digestive system. And our initial results show that organoids remained viable and intact during the mechanical stimulation process. The use of thermoplastic elastomer as a substrate material allowed us to imprint surface topographies such as grid patterns onto flat films using hot embossing. We took our platform a step further and integrate an additional component into our substrates by thermoforming these grid pattern films. This makes our platform a versatile tool for future systematic research, capable of precisely assessing how surface patterns, substrate geometry, and mechanical stimulation collectively influence tissue formation. And finally, in Chapter 7, we focused on creating a controlled concentration gradients. Imagine you are in a room where someone sprays perfume in one corner. The smell is strongest near the source, and it fades away as you move from the source. And this change in intensity happens because of the diffusion of perfume molecules. And that creates a concentration gradient. And in biology, these gradients are very important, especially for organ development. And let's take a development of a kidney as an example. Certain parts of the kidney undergo complex molecular interactions with signaling factors, budding and branching out in specific directions, while other parts are less affected. And identifying the direction in which the branching structures will grow is important to ensure the overall anatomy and function of the kidney. And as I mentioned at the beginning of my presentation, the right signals are needed in the right amounts, placed and at a time. So it's crucial to provide highly controlled local gradients of these signals to organoids, which can guide the directional elongation of new branches. So to generate gradients, we described the integration of thermoformed porous millivalves into microfluidic devices. The porous millivalve in our system serves as a cell culture chamber and acts as an interface between two parallel microfluidic channels, having different fluids represented by blue and red in this illustration. And the porous side walls of the millivalve act as a barrier, regulating the diffusion of molecules from one side of the channel to the other, creating a gradient across the chamber where the cell aggregates are located. And we tested our system by loading kidney organoids into porous millivalve and exposing them to a signaling factor from one side of the channels to induce branching morphogenesis. The organoid remained in its fixed position during the 6-day culture period, and as you can see in the image, it shows budding and branching structures. And I believe that our initial results will open up new possibilities for systematic investigation of the effect of signaling molecules on the directional budding and branching of kidney organoids. So to summarize, my thesis presents the development of novel microengineered systems, which are tools to create complex cellular microenvironments. In the end, these systems expand the available toolkit to tissue engineering and regenerative medicine researchers, and will help the design of functional tissues capable of projecting organ-level responses. With this, I would like to end my presentation by thanking my supervisors, Stefan Gieselbrecht and Roman Trukenmüller, as well as everyone else who has contributed to this research. Thank you for your attention, and now I would like to give word back to Prorector.
Thank you very much for your presentation. We will now start with the opposition, and the opposition will be opened by Professor Moroni, Professor of Biofabrication for Regenerative Medicine at Maastricht University, and he was also chair of the assessment committee.
Thank you, Madam Prorector. Dear candidate, first of all, let me congratulate you with a very nice book, which I read with great pleasure, a lot of interest, and then also extend the compliments to your supervisors. Nonetheless, we are here to question a little bit your work, so that's the job that I will do in the few next minutes. I would like to start with chapter 5. This is actually quite an interesting study, that from a technological point of view, you combine these two technologies, imprinting and electrospinning, as a way of creating micro or nanofibers. Can you then still explain for me the fundamental reason of the combination? Why not just using electrospinning for the microfibers?
Highly esteemed opponent, thank you very much for your kind words and also for your question. In the chapter 5, we indeed wanted to combine electrospinning to increase the potential of the electrospinning, actually, because with electrospinning we can produce fiber textures resemble to tissue matrix. And with electrospinning, it can be produced in a very fast and a large area and really cost-effective way. But because of the conventional electrospinning has a random fiber deposition, which means that the fibers are deposited on the surface randomly, and we cannot really replicate this exact fiber location between the substrates. So it becomes a bit difficult to assess the fiber texture, the
topography, I guess, yeah?
Yeah, on cell behavior. So that's why we wanted to copy these structures and then replicate into this substrate of interest, so that we can produce like hundreds of the same fiber texture on the same substrate. Then it makes us to...
starting from the same template.
Exactly. And then it makes more like statistically robust, it can give us more statistically robust results in the end. Okay.
Now I understand better. Still, I think that with retrospinning you could control the degree of orientation of fibers, but that in a way, if I understand correctly, then using the electrospan mesh as a standardized template, then you can replicate that initial feature on your films over and over again, and that was your starting rationale. Now, what would happen if you have used mostly stiff materials, both for your films as well as your templating mesh with retrospinning. Let's start with the imprinted films. What would happen if you would use elastomers?
I think it's possible. We only used one class of material here indeed, which is thermoplastic. But I believe it's also possible, once you have the mold, it's possible to also imprint those structures onto different class of materials. And thermoplastic elastomers, for instance, it's possible to imprint them using the same mold, for sure. But also the other class of materials, such as like collagen films, by just like not imprinting by solvent casting, for instance, it should be possible.
Would you expect any variations in terms of the nominal features that you...
I believe we need to indeed optimize the parameters of imprinting, because with the elastomers, it might be different than the stiff material. The parameters of imprinting, I mean. We need to optimize it, the temperature, the pressure, or the imprinting time.
How different? Would you expect bigger, smaller features?
A feature size. With optimization, I think feature size, maybe it may not be as deep as the stiff material, because with elastomers, maybe it's better to use a bit...
So the depth will change. Yeah, I think so. I also think that the depth will most likely change.
Yes, but on the other hand, because the fiber sizes that we used here, they are really, the aspect ratios are really not so high. So the diameters are not really super deep. So yeah, we need to try and see, I'll say yes. But in theory, it should be possible.
And would there be a way that you could consider elastomeric substrates as with an additional functionality? I have to be careful on how I frame the question, otherwise I give you already the answer. But with a kind of different functionality, so considering that perhaps the depth would be different, could there be a mechanism that you could consider to apply, since these are much more compliable material that could...
Like mechanical forces, adding the mechanical
for
forces.
example?
Yes, I think that would be really interesting to do indeed. For instance, in one of the chapters, and we showed the mechanical stimulation, and we use an elastomeric material there. And imprinting the same fiber structures onto that elastomeric material, and then applying for instance, a unidirectional or like a biaxial stretching, and assessing the cell response. So which one is more prominent? Is it the surface topography or the mechanical stimulation? Yeah. So I think it would be interesting.
Yeah, that's actually the perfect leeway to my last question, which is indeed, I think in the discussion chapter, you mentioned that in the future you would envision to combine shear stimuli with uniaxial or biaxial stimuli. And so if I look back at your chapter 6 with the intestinal organoids, how would you do that, and why do you think this would be relevant for intestinal organoids?
So I would. So in the chapter 6, we used already maturated organoids, and we only stimulate them at the last phase. So if I would incorporate the surface topographies, then I would do from the start actually, because for organoids to become organoid from the single cells, it's important for them how to come together, and maybe surface topographies might affect this. So that would be something that I would do without just putting directly the organoids, but starting from the beginning.
And where the shear stimuli would help against the more uniaxial or biaxial stretching?
Yes, and then we can still apply the mechanical stimulation after, for instance, 3-4 days when the organoids start a bit more mature. Okay. Then we could apply this mechanical stimulation.
So to stage timely the different maturation of the organoids, if I understand correctly.
Something like that.
And technically speaking, really purely from an engineering point of view, how can I see the shear flow coming into these stretchable films?
What do you mean by that?
Like, if you would have to design now a kind of device, where would be the shear flow coming? Is it going to be
Shear flow, okay. Yeah, for that, with shear flow, yes, you mean like a liquid?
Because I assume that you would transfer to your organoids shear stimuli via shear flow. Am I correct?
Yeah, okay. No, I thought that it's about the mechanical stimulation only. But if you wanted to combine with the shear flow, indeed, then we could put a similar pockets into a microfluidic device.
So the shear flow would be underneath.
Kind of like perfusing it. But for that, yeah, we need to have a porous substrate.
Yeah.
Yeah, with this thermoplastic elastomer, maybe the porosity we could create with some laser structuring techniques. I didn't do it, I didn't see it, but it might be an option to create porous structures and integrate everything into the device.
Okay, thank you. I think my time is up. I'll give back the word to the prorector.
Thank you, Professor Moroni. The opposition will be continued by Dr. Tamasebi Bergani, Assistant Professor at Merlin Institute of Maastricht University.
Thank you very much, Madam Prorector. Dear candidate, I also had a lot of pleasure reading your thesis, and I would like to congratulate you for completing this nice piece of work, and also to your promoter and co-promoter. I do have some questions for you, and as you can imagine, since I share a passion on geometrical features and using them for dictating certain behavior to cells, I would like to start my questions from that topic. So I will continue from where Professor Moroni left on chapter 5. So after you transfer the topography of the electrospun fiber meshes into other surfaces, other polymers, then you actually use another technique, thermoforming, to transfer the topographies onto curved surfaces, so bringing the geometry in one larger scale. What is the effect of microthermoforming on the topographies that you originally started with? Was there any distortion in X, Y, or Z direction?
Yes, esteemed opponent, thank you very much for your kind words and also for your question. And indeed, there was distortion of the topographies, but it was really difficult to assess the effect of this distortion. And it's mainly because it's the curved surface, and imaging those surfaces also does not give really accurate results. So it was difficult to measure. But that's correct, that there was distortion, but it's also because we used two type of molds there, which is one is a long channel and the other one is a cylindrical, right? And the distortions were also different there because of the stretching of the film. So it required quite some optimization. The depth of the film also affected because in the end, the stretching affects the depth. But yeah, like I said, we couldn't really measure the effect of this distortion. But I believe it was not that much dramatic because in the end, when we culture the HUVEX onto the surfaces, then HUVEX still sends the fibers and they still react to fibers and aligns accordingly.
So I understand that maybe within the timeline of the PhD, it is difficult to actually develop all of the technologies, but could you think about one or two inspiring approaches that can be used in future to more accurately measure the topographies on a curved surface?
Yeah, measuring with non-planar surfaces is always not that easy. Well, in my thesis, I mostly used SEM imaging or profilometer. But maybe with electron force microscopy, I'm also not 100% sure how it works with the curved surfaces because I didn't use it. But I know that it gives more accurate results.
Mm-hmm.
Yeah, I just don't know exactly how it would work with this non-planar geometry.
Do you perhaps think a mathematical approach could be helpful here, besides only imaging or physical, where you actually need to have the contact with the surface?
That could be, yes. That's a good point. Actually, that could be something.
Something for your future
maybe.
steps. And in the same chapter, I wanted to actually, this was purely out of curiosity. So following the creation of these nice curved surfaces, you actually chose to put endothelial cells on the surface. And I know that it's likely just to test what is the effect, but when I am looking at these images, so that's figure 6 on page 143 of your thesis. So if you look at the smooth control surface, you see that a very nice monolayer of endothelial cells has been formed. And as you introduce the topography, you will see that that monolayer is disrupted. Is this the effect of topography?
Well, that's a good question, actually. It could be, indeed. But to say that, I believe we need to do more experimental studies. I mean, here, yeah, I didn't really go in depth, but it could be, indeed, that because now the cells are not only feeling the curvature, but they're also feeling the surface topography, right? So maybe it affects their adhesion, but yeah, I cannot really 100% sure about that because...
So maybe in light of these results, do you think that a topography would be, in your opinion, after doing all of these nice experiments, do you think topography would be the right cue to increase the complexity of your culture system for endothelial cells?
Yeah, when you say right cue, then it's a bit difficult to say if it's right or wrong indeed, but it's relevant. So it is still a relevant cue, I would say, and yeah.
Okay. Then I would like to still continue with the same topic, but move to a different chapter, and that is for chapter 4, where then you take the topography of a different tissue and try to simplify that and mimic that onto a substrate. So here, when I look at so this is figure 1 on page 92. If I look at the very nice SCM image that you have on top of the page, so we see ribbons of being elongated across the image. However, if I look carefully, I also see that there are features perpendicular to those ribbons. And you actually chose to only feature one of them onto your substrate, onto the computer design that you have next to that. I was curious why you chose to do that. Here you chose simplicity over complexity, and I'm sure you had a very, very good reason, and I would like to know what that was.
Yes, that's true actually, because in cornea, the collagen lemmas, they are orthogonally arranged. But it is really difficult to make it in 3D, these orthogonally arranged structures. But we also know that once they are aligned, and they can also produce these aligned collagen fibers, so that was the main reason that we simplified it rather than orthogonally arranged structures, but just like looking at the alignment. But what could have been done also is that instead of making these continuous lines, maybe discrete lines, so that there will still some spaces in between, and then the keratocytes might want to align maybe perpendicular to each other, and then maybe they will produce similar collagen fibers.
So there is room for adding complexity.
Definitely,
here.
yes.
Excellent. And a question about the material. You also did quite a lot of material work, so just to pay attention to that. So here you chose a gelatin-based surface to culture the cells on. But I did also a little bit of research and saw that in keratinocyte level, most of the matrix is actually collagen, quite similar to gelatin, but not exactly the same. Could you comment on that what are the additional cues that we might have missed in changing from collagen to gelatin, and particularly with respect to geometry, so sticking to the same theme?
Mm-hmm. Yes, actually the reason that why we chose gelatin is that we didn't want to include unintentional cues to the cells. Mm-hmm. But still, it's not that much far away indeed, because it's still a kind of collagen, a degraded collagen. And that was the reason that's why we covered with the gelatin. And the second part of your question was?
So what I was wondering is that, so it's not only the chemistry between gelatin and collagen, but also the geometry. As you know, collagen has also multiple levels of very nice and naturally formed topographies. And probably they are at a smaller scale than what you try to actually incorporate in your substrate. But do you think that there would have been an effect of those topographies?
Yes, I think there would be definitely an effect. And the effect that we may not decouple as easy as we do here. So that's why we just wanted to, because we use also, we reduce the height of the surface patterns, right? And then in the end, with this zero height, we use a different technique. And we wanted to really create, between all those techniques, we wanted to create the surface as equal as possible for all samples. And that's why if we would add the collagen, then it would also create another effect that might be difficult to decouple.
Thank you very much. I think my time is up, and word back to Madam Prorector.
Thank you very much, Dr. Tamasebi. Then the opposition will be continued by Professor Den Toonder, Professor of Microsystems at Eindhoven University of Technology.
Thank you, Madam Rector. Dear candidates, congratulations with the thesis. I think it adds a couple of nice and interesting and useful things to the toolbox that we can use actually to study biological processes for many applications. And I'd like to focus my question on Chapter 6. Chapter 6, in which you do the mechanical studies and in which you introduce well, a relatively new material for this field, thermoplastic elastomer, TPE. Well, nice results, and we'll come back to the results. But first I want to know more about the material itself, because I didn't find a lot of, let's say, detailed descriptions. I found the name, Hexpol. Somewhere you mentioned usually these are styrenic block copolymers, so I wonder, is this one of them? So can you explain a little bit more, what is this material? What is the chemical nature of this material?
Highly esteemed opponent, thank you very much for your kind words and also for your question. Indeed, I didn't put a lot of detail about the material, and the main reason is that the material is a commercial material, and they also didn't share that much information about the structure. And what I know is that it's SEPS, so styrene ethylene butylene styrene copolymer, and it's highly elastomeric, thermoplastic elastomer in the end, and that was the reason that I didn't include. And to be honest, I also don't know the exact chemical structure and so on.
Okay, that's interesting. So commercial polymer, right? A commercial material. Did you consider any alternatives then? Or was this just, you picked this one from the catalog and that's it? Because there are alternatives.
Yeah, that's true, there are alternatives. But in the end, even if with the alternative materials, I believe polyurethane is also used very often as a with such applications. So this could be another option indeed. But we had opportunity to use this material, and also because with the catalog, there were also other properties that we could choose in between. And we choose, for instance, this is the oil-free version of that material. And for other applications, there are also...
Okay, then going to the properties, because I think you show measurements, actually, you did measure properties also of the material itself. Figure 2, page 170, you show the elastic properties, let's say, or the mechanical deformation properties, and you show contact angle measurements. So you say something about surface energy. You compare it with typical properties of PDMS, right? So it's slightly hydrophobic, but not as much as the PDMS. It's way more, let's say, deformable than PDMS. But I was missing something else, which is optical properties. So how about optical transparency of this material, or maybe even autofluorescence? Because we always use microscopy, right, to look at cells and tissues and organoids in these systems. So can you say something about this?
Yes, that's a very valid question indeed. I have to say that with the optical properties, well, it is transparent, but with the thickness that I used the material, it was not as transparent as PDMS. And because we didn't do staining, immunofluorescent staining, I'm not 100% sure about this the background noise that it will create or some autofluorescence it will create. But what I know is that they also use the same material in, well, maybe it's not the same, but maybe different formula, but still in cell culture applications. So I believe it should be possible to find the formula with less autofluorescent maybe, but because I didn't try by myself, I didn't test, so I cannot really 100% be sure.
Okay. And this material, do you need to coat it before you actually continue to cell culture or organoid culture?
We didn't coat it,
okay.
But I believe it's possible to also coat if it's necessary. But for our application, because it was a free-floating aggregate, and we didn't have to really coat it.
Yeah. Okay, so then turning to the results of chapter 6, most of the results that you show are still flat surfaces, right? So still 2D-like. You show some initial experimentation using the actual millibells, as you call them, right? So which would provide you the real 3D, basically, configuration, and you showed it also in your presentation. What are the challenges to go there? Because I think, at least it's not reported in the thesis, I believe, right? So that you have organoids or any other biological experiments within those millibells. What would be your challenges to go there? Because I don't think it's trivial.
Well, it may seem like it's not trivial, but it will still require some optimization to come that point. And the main reason is that because of the film thickness, because also you could create a different thickness of the films, which is also affecting the thermoforming process.
Okay.
So that's why we had to do some optimization in the beginning by using different film thicknesses and thermoforming processes.
And then you optimize for what? What is then the optimization criterion?
So in the end, it was to be able to thermoform with like as higher yield as possible, let's say, because after a certain point, when the thickness is decreasing, then it became also difficult to thermoform, but it might also be because of our mold, so yeah, I cannot really also like 100% say that it's just because of the thickness, because then it becomes a rupture, maybe, around the wells and so on. And if it's so thick, then it again becomes difficult, because then it's not really flowing inside the cavities.
Okay. So there are still quite some challenges also, even, I mean, you solved many of them in terms of fabrication, but I was thinking about something else, because you still need to transfer your deformation, your strain, to the organoid that's there, right? And I guess it's within a gel. I think you used Matrigel, probably. So how do you make sure, so how should I translate that deformation of your midwell to the actual deformation or stress or whatever you want to call it in the organoid? Yeah,
so actually it's a very good question, and because the organoid in the end, the stress that it feels comes from the material transfers to the gel, and gel transfers to the organoid. So in the end, okay, we know how much strain and we are applying to material, but we actually don't know what's going on inside the gel and how it transfers. So I believe this is something that not really easily can be done by experimental to measure, but maybe some modeling, some simulations could be really helpful. And for that, then you also need to know, of course, the Matrigel very well, or the gel of interest that you are using, because it will also highly affect how it's going to transfer all this stress into the organoid. So I believe then maybe modeling or some simulations would be really helpful to understand what organoid is feeling actually.
I'm not sure if you had the issue in the 2D, because in the 2D you also use Matrigel, right? So if we do complex geometries and we transfer strains or forces to hydrogels, we often see that the adhesion actually between the hydrogel and the material itself turns out to be a problem. Do you see that also? For example, maybe you've observed that in your two-dimensional experiments, that the adhesion of the gel actually is relatively weak. And that means actually you break just the interface and there's no transfer of strains at all. Is that something that you observed, or is that not really happening
Yeah, the
with this
cell
material?
culture experiments I didn't perform by myself, but my colleagues did. And yeah, as far as I'm aware, that there was no problem with this, because we also consider this actually that might be a problem.
Okay.
But as far as I'm aware, that she didn't observe such issue.
Okay. That's good to know. Okay, thank you very much. Thank you.
Thank you, Professor Den Toonder. The opposition will be continued by Professor Kallio, Professor of Biomedical Engineering at Tampere University in Tampere, Finland.
Thank you. Also, congratulations from my side. It was a pleasure to read, well written, and congratulations to promoter and co-promoter. I would maybe continue a more general question that is actually related to your last answer. As we know, science is nowadays multidisciplinary, and cooperation is needed. And also in your experimental chapters, there are other researchers. So what has been your role? If you briefly summarize your role in these experimental chapters, what was your contribution?
Highly esteemed opponent, thank you very much for your kind words and also for your question. My contribution here was mainly to develop the system, develop the platforms, so engineering side of the platforms. So I combined the techniques and also the materials so that I could develop a bit more complex environment for cells, or more controlled environment for cells. And my collaborators, which you see in the as co-authors of the chapters, they were mostly performed cell culture studies.
Okay. Okay. Have you been participating in the cell culture experiments?
Have I been?
Did you participate in the cell culture experiments by yourself?
Yeah, only in one of the chapters. I believe it was chapter 5. I did UX by myself, and it was already difficult enough for me to do, actually. But other than that, yeah, I just know from their experimental process and then the results that we discussed together. But I didn't do the cell cultures by myself.
Okay, thank you. If you go then to chapter 5, and I think if you show one of your images of your presentation on chapter 5, where you had the fibers, maybe you can share it if you show that. One before. Here. So I think you base your conclusions on measuring the dimensions of the fibers.
Yes.
From these kind of images, where the fibers are crossing each other on top of each other. So what is not very clear to me now, that when you report the standard deviations, are they because of measurement uncertainties or because of uncertainties in the production? So if you elaborate, how did you measure these dimensions, and what is your own estimate of the error or the uncertainty in the measurement itself?
Mm-hmm. So indeed, I use this SEM images while measuring, and with the image J, I measure the diameters, and I try to measure as random as possible, and from the different locations. Yeah, I could have done this with this automatic measurements maybe, but it was not really, it didn't really work with this imprint films because it was really difficult to detect the fiber diameter. It might be indeed because of the errors, the deviation might also come from the measurement technique that I used indeed, because it's a bit like a human error might also include there, because I'm just selecting the diameters by myself. To make it even more precise, maybe again we could use something like AFM, but then it would take so much time to measure such a large area, I assume, because it really goes with the nano size. But I would say that still, even if there are deviations, so the measurement still gives a quite close idea about what you are obtaining, because in the end you are not going to measure something like, for instance, if it's 0.5 micrometer, you will not measure it as 0.8 or 9 in the end. So maybe 0.55 Yeah.
Yeah.
So in the end, it would come to the, it would be as close as.
So basically, the measurement error is smaller than the deviation in the fabrication.
Could be.
Yeah. Okay. If we then look at chapter 6, we a little bit discussed it in previous questions already, but maybe a similar type of question. That what do you think that are the main sources of uncertainties in your experiments? If you think that you apply from pressure, changes, this is your input, and then your output is that you are looking at the organoids and what are the changes in the organoids. So what do you think, what are the main uncertainties here in this process?
Yeah, I think as we discussed before, I would say that because we don't know how it transfers to the organoids. So that's one of the main issue, I would say.
And maybe another thing that also, is there a difference between the flat and between the millivals in these uncertainties?
Yes, I believe there are differences because with the flat film, with the millival films, especially when it's, for instance, unidirectional, you are actually really squeezing from one side, and then the other side is kind of like elongating, right? So it gives a bit more room for organoids to go to the other side and then squeeze from the one side. But with the flat films, you are actually relying on the transfer of these forces from hydrogel to the organoids. Because these organoids are not really adhered to the surface. They are just like floating inside the gel. So that's the main difference, I believe, with these millivals and the flat films. Yeah, with the flat films, the uncertainty would be that because they are just like random inside, so even if we know how gel transfers the mechanical forces, we still cannot be sure because they are in the different plane. Yeah, some are really close to the bottom, some are like really close to the top inside the hydrogel. Then it really makes it difficult to estimate what they are really feeling it.
Because I think it's location dependent as well.
Sorry?
It's also location dependent.
Definitely location
And maybe
dependent.
one more question on this is that, referring to Professor Moroni's question, what we have noticed, or when we have simulated stretching devices, we see that when you stretch, it's not only stretch, but there's also flow because of generated by the stretching. Especially if you have medium. What is your comment on that? Can there be also flow generated because of the cyclic movement?
Yeah, that's true. I think definitely there could be an effect of that. But for that, again, I would say that some maybe simulations would be helpful to investigate, because these are really difficult to do experimentally. So simulations would definitely be helpful.
Yeah. I think almost impossible experimentally.
Yeah, probably. I mean, I wouldn't want to say really as bold as that, but yeah, true.
Thank you, Professor Kallio. We come now to the last opponent. It's Dr. Caiado De Carli, Assistant Professor at the Department of Biomaterials and Biomedical Technology at the University Medical Center in Groningen.
Thank you, dear candidate. I would like to congratulate you about your beautiful thesis. I learned a lot and I enjoy a lot the reading. I also want to congratulate your both supervisors. So I would like to ask you one of your paronyms, please, to read proposition number 6.
The widespread adoption of microengineered systems depends on both the quality and quantity of biological data.
Yes, thank you. So I fully much agree with this, but considering what you discussed before about simplicity and complexity, this one I think is a bit simple. And I would like to ask your opinion now, after working almost a year in a spin-off company in product development of this kind of systems, what else do you really think that you need to consider for your system to being adopted for the scientific community?
Hi, esteemed opponent, thank you very much for your kind words and for your question. So if I understand correctly, you are asking that which quality or quantity of the data is important to adapt?
Not only data, but what else you think in your systems that you develop, what else is important besides data for the society to really adopt your system?
So I believe that for researchers to adopt a platform in general, the platform really needs to prove itself, and it really needs to prove the reliable data, needs to generate reliable data, and it needs to show maybe equivalent or even superior property, properties, more than, for instance, animal testing. So that's why, for this reason, when a new platform is developed, it's really important to also test with maybe different, if it's suitable, different type of cell models, organoid models, and to test that if we can get reliable results. This is one point, and the other point is that the platforms that we developed should be easy to use for other researchers as well. So it shouldn't really deviate from one lab to another. So because we are here want to really control this microenvironment, but if this microenvironment deviates from one lab to another, then in the end it's not going to be that much controlled. So I believe these two.
Yes. You answered very well. Yeah, because I believe sometimes as engineers we need to offer a tool, but this tool should be implemented, right? So we need to find an unmet need to apply that. Yes, very well. So my next question I have is in the chapter 3. Actually, in the future directions of this chapter, because I didn't see much about this, that's why I want to ask you about the biodegradability of your materials, of the films that you made, especially considering different applications. So to thinking on translation, how do you see the biodegradability of your materials?
The materials that I used, they are not really for implanting, but they are mostly for in vitro screening purposes. So for this reason, I think it really won't be that much relevant with the biodegradability, because we wanted to create the platforms that we can screen the cells in a high throughput manner.
Yeah, but for example, if you culture the cells for a long period for producing a protein or something, for example, maybe it will be important to know if your material is not releasing something over a long period of culture, for example. So you take this in consideration as well?
But do you mean that it comes from the interaction between the substrate material that I produce and the material that is released?
Yes.
Yeah, I believe these materials that I used in the thesis, they are not really comes in, or they don't really interact that much, or at least that I didn't really see any interaction. So I believe that in this sense, it should be inert. They should be inert.
Okay. Thank you. My next question is also in chapter 4, is a little bit of my other colleague already asked about the gelatin and the collagen using as coating. So I would like not to go for the biological side of what's the difference between these two, but more for the technical point of view, because you do these beautiful topographies and microarchitectures. So how much the coating can affect this in terms of, did you control the thickness of this coating? And if you change to other types of proteins, how much does affect your topography?
Yeah, that's a good question. Indeed, we didn't check the thickness of the coating, but it's mainly because we also did other coatings with other topographies, and it really didn't increase dramatically. Yeah. It's because these coatings are really thin. So we mostly put the material, and then we incubate onto the substrate, and afterwards we flushed or just like clean the rest over. So our assumption is that it's really like the really thin coating on the surface that will not really affect that much dramatically to the surface textures. And also because, here with these topographies in this chapter, they are still in the micro size. They are quite large and big. But for instance, I did the same coating with electrospon fibers, and they are almost like 0.5 micrometer, around 0.5 micrometer. And that was one of my actually concern, that what if when I coat them, if the cells don't feel the surface at all? But in the end, it was not the case. So coating was really in a small or thin layer that did not really affect that much.
Oh, that's very good. So this also gives you freedom, right, to try many different of proteins depending of the cell that you're using.
Yes.
And you can control this thickness. That's good. So if I may, can I have a very last question? Yes? Okay, thank you. So about the impact of your thesis, again, coming back to product development, because it's very nice you could show many different engineering strategies here, so I think it's really nice to think how we can implement this. And I observed in your thesis that you pretty much focus on tissue engineering, regenerative medicine applications, of course, but I can clearly see another very big field that you can apply your devices. Can you discuss a little bit about that? What would be another topic that you really believe that your devices could make a change?
Yeah, so it could be for pharmaceutical companies, for instance, that could also test their drug development and test the cells with these platforms.
And a question regarding this. Did you have it analyze the surface area of your materials, comparing if you just have a 2D simple monolayer? Because on this case, I expect you would have an increase, so you also can offer this as a way to culture much more cells than a traditional 2D substrate. So you can also culture cells to produce, for example, very high difficult to express proteins, recombinant proteins, for example.
Yeah, because I didn't do the cell culture experiments by myself, so I didn't really have opportunity to test it. But this could be something to use.
Thank you very much. Gözde Şahin, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. I know what's on the line. I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Hit the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
Please be seated.
Gözde Şahin, the degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Dr. Stefan Gieselbrecht is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
All right.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent and responsible?
Yes, I do.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Gözde Şahin, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university.
Ladies and gentlemen, esteemed colleagues, friends, and family of our newly appointed doctor. Today we celebrate a truly remarkable achievement, the successful defense of Gözde's, of your doctoral thesis. This is an important milestone, not just in your academic career, but also in your personal journey as well. And I would like to begin by extending my heartfelt congratulations on your achievement. So your journey with us started in a rather unexpected way, I would say. Back in 2018, you sent an unsolicited application for a position actually at KIT, so Karlsruhe Institute of Technology, my previous institution where I've worked. And even though I had already left the institution 4 years earlier, by sheer luck, my email account was still active. So thanks to this fortunate twist of fate, your application still landed in my inbox. And then with Roman and Nello, we discussed your background and the work you had done during your master thesis at the Middle East Technical University, where you had already developed impressive skills in the fabrication of microparticles. We quickly realized that your expertise would be a perfect fit for the ambitious work we had planned for the eyesight project. Soon after, you were hired, and in October 2018, you officially joined the team at Merlin. From the outset, your PhD was part of an extensive and complex project involving multiple collaborators from various institutes, all working towards new treatments of the human cornea. And while the project itself was a monumental task, the environment in which you were working didn't make things any easier. So throughout your PhD, you were exposed to rough waters in the form of both pandemic and the severe cyber attack that hit our computational systems. And being part of a large consortium with, well, where you have 10 to 15 people usually meeting virtually, project communication became quite difficult. Yet, despite these obstacles, you remained focused and determined to push forward, adapting to the challenges while maintaining a strong sense of productivity. And that was for sure a test of your resilience, but you passed with flying colors. You came to us as a chemical engineer, tasked with applying your skills to the highly specialized field of eye research, a shift that wasn't without its challenges. Our task in the eyesight project aimed to fabricate complex microstructures for the treatment of the human cornea, and we sought to use nano and microtopographies to create instructive surfaces and scaffolds for these corneal, endothelial, and stromal cells. And this was, for you, certainly a steep learning curve, but you managed it with grace. And in a very multidisciplinary team, you were focused on new engineered substrates for treating corneal diseases, experimenting with different techniques to create such instructive surfaces for cells. And your approach was always strategic and creative, always trying to find the best way to contribute your engineering expertise to this complex biomedical problem. Yet, as we continued the journey together, your scientific project grew and evolved. So after the official end of the eyesight project, we broadened the scope of your thesis, allowing more flexibility in research. And you actually took the opportunity to explore some biological questions yourself. I remember how intrigued you were by the biology behind the work we're doing, wanting to dive deeper into it. However, I think you quickly realized that culturing and analyzing cells can be a slow and painstaking process. You managed to complete these experiments, but you probably also found that it wasn't where your true passion lay. Instead, you returned to the engineering side of things, applying your skills in more familiar yet equally innovative ways. In addition to the core research chapters, we also worked together to develop 2 review chapters. Especially the second one turned out to be a considerable challenge, but one you met head-on. The review you've put together is now an impressive, comprehensive overview of many technologies that can be combined to fabricate multi-scaled structures with instructive features on complex 3D surfaces. It is not submitted yet, but it is already a testament to your hard work and also to your ability to synthesize and interpret vast amounts of scientific literature, a skill that will serve you well also in your future career. But your achievements go beyond your scientific output. What stands out to me and to your colleagues and our colleagues is how enjoyable it has been to work with you. The people in my team and myself always appreciated your insights, feedback, and help. You've always been open to exploring new ideas, whether that's experimenting with different techniques in the lab or being one of the first in our group to embrace generative AI tools to create colorful scientific illustrations for your scientific papers. You brought the same spirit of curiosity to everything you did, whether it was work-related or not. You even started new challenging projects with other team members in your spare time. On top of your academic and professional commitments, you've always managed to keep up with your love for outdoor activities and sports. Whether hiking, mountain biking, or training for a rowing contest on the River Maas, you demonstrated perseverance and commitment, even getting up before dawn to row. I believe these qualities, your motivation, your discipline, and your passion, have helped you succeed both in the lab and in life. Now, as we gather to celebrate this incredible achievement, I would like to take a moment to acknowledge the assessment and defense committees. Your feedback and guidance have been invaluable, and we thank you for your time and effort. And finally, dear Gözde, or I should now say Dr. Şahin, my heartfelt congratulations. This PhD journey may have had its shares of challenges, but you navigated and rode around them with grace, determination, and a positive spirit. As you move forward, I am confident that the same resilience and curiosity that brought you success here will serve you well in whatever challenges lie ahead. Just as you have shown today that small features can have a great impact, I know that in the future, even the smallest actions and decisions you make will lead to significant achievements. Congratulations to you and your family on this incredible milestone. We, and I'm speaking on behalf of the whole supervision team, are all very proud of you.
Yeah, dear Dr. Şahin, also on behalf of Maastricht University, I would like to congratulate you with the degree you have acquired. It's an important day, a milestone, I think. Of course, I also congratulate your family, your friends and colleagues who all supported you during this PhD trajectory. I know they are very important to keep everything going. I congratulate your supervisor with this nice PhD defense. I'd like to thank the members of the degree committee for the work they did for this PhD defense and their presence here, especially our guests from outside Maastricht University, Professor Nentonder, Professor Kallio, and Dr. Caiado de Cali. Thank you very much for coming to Maastricht to take part in this PhD defense ceremony. I can tell you that the committee was very much satisfied with the way you defended your thesis. I was also very happy with your introduction, because I'm not an expert in this field, but you were able to explain very clearly what you've done and the main findings of your research and the importance of the research. And I hope that you also look back with satisfaction on this PhD defense. It's now time to relax, enjoy, and I think we'll start that in the rafter. But first I will close this academic ceremony.